the circle. So here's our chord. Then we talked about what a radius is. A radius is something that goes from the center and ends on our circle. Remember, our radius can be spun around anywhere, and it's always the same length. Then we talked about a diameter. A diameter is a very special chord that goes through the center of the circle. I do want to point out that a diameter is actually made up of two radiuses, or radii. So that's a radius, makes a diameter. A diameter also cuts our circle in half into a semicircle. What's the measure of a semicircle in degrees? 180 degrees, because the circle is 360. Then we started talking about arcs, so that got us talking about arcs of the semicircle going halfway around. We have things called minor arcs and major arcs. A minor arc is one that's less than 180. It's the quickest way between 2 points. The longer way is our major arc. That's going to be bigger than 180. As a reminder, to say what a minor arc is, we always use that arc symbol on top, and we use 2 letters. So that minor arc right there we would call arc AB. A major arc uses 3 letters, so if I wanted to do that one, I would do ACB, would make that a major arc. Within this drawing is also a central angle. A central angle is made up of 2 radii. It is an angle that goes to exactly the center of the circle. Then we also learned about ones that were made of chords. These are 2 chords making an angle. In other words, what I like to picture is this is an angle that's at the back of the circle. Not in the middle. It goes to an edge of our circle, comes here. That is known as an inscribed angle. We also learned tangent lines. I guess I didn't put that on here, but just a reminder, a tangent line is something that looks like that just touches once on a circle. That is our tangent line. In that nutshell is basically what we learned yesterday. So today we're going to expand upon this. I do want to talk about real quick again our pacing of this, chapter. That we have 3 lessons next week: Monday, Tuesday, Wednesday. On Wednesday is a no homework weekend, so you don't have to do that homework. When we come back on Tuesday, we'll have a work day to finish that homework. Then we'll have a review day, and then we'll have a test day. That is kind of our flow as we go. I didn't even mean that to rhyme. Anyway, it works. Anyway, I do want to specify this chapter is a lot of kind of memorizing properties and things we just have to keep straight. And that starts with the difference between a central angle and an inscribed angle. So we start talking about a central angle. The big thing you need to know about a central angle is A, it's made of 2 radii, which means both of these lengths need to be the same. I'm actually going to put those marks on there. So we know that both of these lengths are the same. If it was a triangle by isosceles, but it's not an isosceles, it is a central angle. The central angle property says that whatever measure the angle is matches the arc it subtends, or that arc it forms. Both of those measures are always the same, as long as it's a central angle. So, for example, if I'm trying to find this y here, I'm going to say that's a central angle. That, for a fact, is a central angle. So we do have a central angle, and so that means that's going to be the same measure as the arc that it subtends. So I just need to figure out what this y value is, and this will match that value as well. So this, allowing me to put it on the outside, allows me to match it up with this 120 and 155. How does that help me solve this problem, though? Yeah.
A full circle is 360 degrees.
A full circle is 360 degrees. So how am I going to find the measure of just this arc here? And maybe I'll just... So we now know that the entire circle is 360. How do I find that little orange arc right there then? What do I plug in my calculator? Yeah.
Oh, it's 85.
It's 85?
Yeah.
How'd you come up with 85?
Add 155 and 120 together.
Mm-hmm.
Then, that makes 275 and then subtract it from 360.
Yeah, we just do 360 minus that 120 minus that 155 to give us 85. And like I said, these two measures must be the same. So if the arc is 85, then our central angle is also 85. Now let's change this color to black. I do want to make a small change in the next one. It was just me making it incorrectly. Can we picture this as just being a straight line? Just kind of picture it looking like this, where that's a straight line to be. I want those to be vertical angles. I want those to be vertical angles. That was the point of it. I think I got a little wonky when I drew it. Those should be vertical angles. These two should be vertical angles. All right, so now if we kind of picture that, so even though it doesn't look like it, those are vertical angles. If I tell you right now they're vertical angles, okay? Quit arguing with me. I'll crush your soul. All right, let us keep track of the fact that those are vertical angles when I'm asking you to find this arc. I'm asked to find that arc FD. Well, what I'm going to note is, first of all, I know a big chunk of it. I already know a big chunk of it. I know that this 81 is going to be the measure of this part of the arc. So that right there is 81 degrees. And since I do have all these degrees labeled in here, maybe it's going to help me find all of these interior ones and then throw them out. So what I'm kind of picturing is, what if we find this measure and then we'll know that arc? How do I do that? Now that I cheated and showed you that one. Yeah.
You subtract 135 by, or you subtract 180 by 135.
Yeah.
The EB is like 590.
Yeah.
So angle 180 plus 5.
Yeah. So we're going to do that 180 minus that 135. So that should be 45, right? And now that I said that these were vertical angles, we would know that this one's 45.
I got 54. I went true.
Say that again? I'm sorry?
Oh, I'm true. Wait, man? Yeah,
Dan just goes, yeah. So we got that this is 45, right? Yeah, you sure? Okay, so that's 45, which makes this 45, which we can shoot straight across, so this is 45. And then I'm guessing we're going to have 126 degrees all the way through. Good? Happy? Not too hard. Central angle is equal. It's just going to be hard when we have big drawings and we have to remember this. So central angles equal the arc they subtend. Now let's talk about an inscribed angle property. Now, what I want us to kind of remember is the farther you are away from an object, the smaller the angle is to get there. So if we kind of picture me hugging this board, my arms have a pretty big angle here. But if my arms stretched and I kept them on that board, the further I walk away, the smaller my angle is with my body. Does that make sense? The closer you get, the bigger my arms have to get to it. So it wouldn't make sense if an inscribed angle was the same thing as a central angle. Central angle was equal. So what we're going to find out now is that an inscribed angle is actually half the size of the arc it subtends. In other words, if you know your inscribed angle, you double it to find that arc it subtends. If I tell you your arc, you divide it by 2, and that will give you the angle of, or the degree measure of the angle that forms it. So your big thing is 2 when you're thinking about an inscribed angle. It doubles to go out, you have it to come back. So if this arc is 80 degrees, what is that inscribed angle that forms it?
You divide it by 2.
Mm-hmm. And what is that?
40.
What was that? 40. So we're going to have 40 degrees. So to come in, we just divide by 2. So coming in would be 80 divided by 2 would give me my W. Now, you can imagine on the test it's not just going to be straight up find those. We'll have ones that we have kind of a complicated picture. But what I want us to always realize is that if I give you a measure of an angle, figure out what that angle forms. So I'm going to highlight that in red. Well, that's an inscribed angle. That's an inscribed angle. And it says we're supposed to somehow use that fact to come up with PD. Well, arc PD is this arc here. How does that help me? What do I do next? Jacob?
Well, if on FP,
Mhm.
it's 70.
So that's 70 degrees, yeah. So that arc is 70 degrees. How does that help me get my PD? So you're on the right path. Yeah.
Angle FDP is 35 degrees.
FPD is 35 degrees?
FDP.
FDP. Oh, yeah, it would be 35 degrees. That is true. But I'm looking for that orange. We are going to need that fact in a while. That is a good fact to realize. Joaquin.
You know that FPD is, what's it, a semicircle?
A semicircle. And what's the measure of a semicircle?
180, so it's the 180 minus 70.
Yeah, so if all of that's 180, I just have to do 180 minus that 70. That must be 110, right? Only 110 degrees. Questions on that? You actually discovered a theorem we're going to talk about later, that if two inscribed angles form the same arc, that they're equal to each other. So it's nice that we saw that. All right, those are kind of the easy ones for today. Those are the easy ones. Now we're going to get to more complicated ones. They're complicated. It just kind of takes practice. It takes practice. It's going to be kind of, if you see this, you have to think this. If you see this, you have to think that. So the first thing we're going to look at is, if you ever see two chords are the exact same length. If two chords are ever the same length, the arcs they subtend are also equal to each other. So this distance from C to D is the same in the chord and in the arcs then. And notice how my arrows go both directions. That makes an if and only if. So that means if you ever see arcs that are equal, it means the chords that make them are also equal. So they're either both equal or neither of them are equal. Does that make sense? Either the arcs and the chords that make them are equal, or none of them are equal. So once again, if you see marks on chords, you're looking at the arcs. If you see marks on arcs, you're looking at the chords to say that they are congruent as well. Does that make sense? Okay. Now, the next one that's a little more complicated is, this says the perpendicular bisector of a chord is a diameter or radius of a circle. Here's my advice for you. So if you ever see a 90-degree symbol on your circle, it means something important. Yes? Wouldn't the other side equal 90? What other side? All the other angles would equal 90 as well. Yes. But I do want us to, as soon as we see a 90-degree angle, it's going to basically, so we have a 90-degree angle right here. If we see these two congruent signs, that automatically makes this line a diameter. Automatically. So we don't even need to see this point right here. If I see a 90-degree angle, and two congruent symbols, that automatically makes it a diameter. Now, usually we don't care about this direction. This isn't the most important thing. What I want us to look out for is a diameter with a 90-degree angle. That's what I want you to start looking out for. A 90-degree angle formed with a diameter always is going to bisect this chord. This is honestly the picture you should look out for. Once again, you're looking for a 90-degree angle that's a diameter will bisect this. So if I see this, I'm going to put the tick marks on here. In fact, that's how I started this one. So I already helped you out on this one because This is a radius, just like a diameter, it goes from the center. It formed a 90-degree angle, so that automatically means that it bisects this chord. This is a 90-degree angle, it bisects this chord. So technically, just go with me here for a second, don't write this on your sheet. Technically, right now, without any other theorems, this is as far as we could go. 90-degree angle, radius, means it bisects it. Doesn't mean they're all the same, but it means it bisects it. What this one adds to it is, if this happens to two lines, so if we see that 90-degree angle going to the center, and it happens to two different chords in the same drawing, we can pull some information from it. First of all, if I see a radius or something connected to the circle and 90 degrees, we know it cuts it in half. Well, if it turns out that these two chords are the same length, maybe we could put tick marks on the outside. So that length, put double ticks on it, is the same as this length. So if we see that 90 degree centers and both of these chords are the same length, we can actually know that they're the same distance from the circle, so we can put tick marks on these. We can also go the opposite direction. If you see those 90-degree angles, like I said, you have to look out for 90-degree angles, and you see tick marks on both these lines, we can go back to this one and say that AB is congruent to CD. So that says two chords are congruent if and only if they are equidistant from the center. One more time. If you see a 90-degree angle and something going to the center, you split it apart as being equal. If you see two of them, you're looking to see if they tell you the chords are congruent. If they are, the distances are congruent. If you see your 90-degree angles and you see your distances are congruent, that means your chords are congruent. This stuff can get very confusing. You have to go back to these pictures and see what matches up the best you can. The big thing is you're always looking out for 90-degree angles. That's the first thing in drawings. And then ask yourself, why is it important in this drawing? So let's do an example of that. So I see two 90-degree angles. That means it's not guaranteed to be this one, but this is the picture I'm looking for. All right, so we have two 90-degree angles. Here's the first thing I know for a fact. There's a 90-degree angle connecting to the center, so that automatically means that they bisect these chords. So that 90-degree angle tells you it bisects those chords by this rule. Center, 90 degrees, bisects. Then we keep reading, and it actually says that DE is equal to JK. So what can I change from this drawing now that I know that DE is congruent to JK? Yeah.
That JZ is equal to DY.
Yeah, JZ is equal to DY, so I can actually remove one of those tick marks and just make it a tick mark, which means this one also has to be just a tick mark. So we can erase, we're using pencil. We can go 90 degrees, bisect, bisect. Let's put that in. And then when we learn more information that DE is congruent to JK, I can go, oh, that means all of the segments are congruent. So I can go ahead and do that. Based upon that new information that DE is congruent to JK, what else could I add to this picture without reading anything else? Yeah.
That XY and XZ are congruent.
XY and XZ are congruent. Because we have that rule that if these chords are equal, the distance from the center are also equal. That came from this third one. So you're going to see these 90-degree symbols are going to relate to both or one of those things from above. You just have to notice 90-degree angles and figure out which one matches. All right, let's keep reading. So it says JK equals 30. So this distance equals 30. What should I probably do with that 30? split it. So I should think about this as being 15 and this being 15. Because then they go further and say that jx equals 17. Well, that makes this 17. I need to find yx, but yx is the same thing as xz. How does that help me? How does it help me to know I just need to find xz? How do I find xz? Let's see if one person remembers the entire chapter we just did. Crystal? A squared plus b squared equals c squared. This is a right triangle. We're going to snag this right triangle and pull it out here and go, oh, okay, that's a right triangle. And we have a hypotenuse of 17. We have a base of 15. Is that a Pythagorean triple? Is there something that's something 15, 17? What was that? It's a good guess because we do have a 12 one. It's not a 12 one. It's 8. It actually is a... What if you don't remember Pythagorean triples? Is it okay to do a squared plus b squared equals c squared? Absolutely. So either you remember that this is equal to 8 by the Pythagorean triple, or we just go, oh, that's just x squared plus 15 squared equals 17 squared. I bet you if you did that math, you're going to find out that x equals 8. Well, doesn't that mean that xy is 8? Yeah. If xz is 8, then xy is also 8. So we'll just go xy equals 8. Those aren't the worst ones. The worst ones are where you have to draw it. Honestly, because they don't give you all the information, and you have to figure out information from what you're drawing. So we're going to do one where we're drawing together. So those are going to be the hardest ones on your homework. They're like the last 4 where you have to draw specific questions. Okay, so we start with circle C. So let's go ahead and label this as C. Then they tell us there's a chord AB. Well, chord AB could be a diameter, technically. I'm probably not going to draw it as a diameter until I find out for a fact is it a diameter. In fact, if I drew this as a diameter, I'd have a problem because it says it's 12 centimeters from C. Why can't that be a diameter then? Why do we know for a fact that AB is not a diameter? Okay. Yeah, it's basically saying it's 12 centimeters away from being a diameter. So we're just going to draw a chord anywhere. I usually just draw on the right. I don't know why. You could draw on the left if you want to, but I'm going to draw it there. We could draw on the top. We could draw on the bottom. Doesn't matter. Okay, so we know that's 12 centimeters to C. Now, just as a reminder, when you measure something, you do it as a 90-degree angle. If you have a contractor that's building something and you tell them to put it like 15 feet away from the wall, well, they're not going to take their ruler and like at an angle measure going down. That's not what we want. They would go 90 degrees from the wall and just keep adding from 90 degrees. So when I tell you something's a certain distance away, you always have to put a 90-degree symbol on it. So the distance from here to here is 12. So that's the first thing we're going to do. Then they tell us that the radius of C is 18 centimeters. Just a reminder, radius goes from the center to the edge of the circle. So this is usually the first place that people will put the radius. They'll go, okay, my radius is there. It's 18. So together this would be 18, which would make this 6. And it seems like we're getting somewhere, except for the fact that doesn't help me find AB. And I guess I should label AB real quick. That doesn't help me find AB. So what do we do instead? I want a different place to put the radius. I want us all to just picture where we would put the radius. Think about this. Don't just wait for someone to answer, because I do see hands up. I'll call on someone in a second. But I want you to sit there and think, where would you draw a radius that might actually help you solve this? And my hint is we spent several weeks learning how to solve right triangles. Ella, where do I draw that radius?
Either from C to B or C to A.
Yeah, I'm going to do C to A just because I have all that crap down there. So I'm going to draw it up here. I'm going to go, let's do this in pink like I did the other one. I'm going to draw it up there. Because we know that radius is 18. And look what we have. We now have a right triangle where we can find this missing... Oof. I'm going to label this D real quick so you know what I'm talking about. Do we know anything about the distance from A to D and D to B? Are they related at all? Jake?
That, congruent.
They're congruent. Do you know how you know it's congruent? Because the perpendicular line go to the center automatically makes it a bisector. So now we know A to D equals D to B. We have a right triangle here. We have a right triangle here. And so we're just trying to find that length. And it shows up in 2 places. So I multiply by 2 when I get to the end. So we're going to have x squared plus 12 squared equals 18 squared. Is that a Pythagorean triple? It is not. It is not. It's not going to come out to a nice whole number. In fact, if we just kind of work our way down, you could double check my math, but I think this ends up being the square root of 160. 180? Oof. Thank you. My math in my head gets fuzzy at times. 180 is a pretty big number, right? Is there a chance that this is simplifiable? Is there a perfect square that goes into 180? No.
Oh, no, not perfect square.
Is there a perfect square that goes into it?
Yeah, 36.
36 does go into it. 36 does go into 180. If you just take your calculator and just plug that in, well, we're going to see that 180 equals the square root of 36 times the square root of 5, which equals 6 square root of 5. What happens when you have 6 square root of 5 plus 6 square root of 5? What was that? 12 square root of 5. So our answer from A to B is 12 square root of 5. We're done. Questions on that one? My hint to you on some of the harder ones, when you're drawing them, you're going to be required to draw a central angle. That is my hint on the ones that you're drawing. If you're stuck, think about, does drawing a central angle help you? That is my advice to that. All right,